So can you see the screen?
Yes. Yes.
Okay.
I can
So
see the
let's
screen.
start.
Yeah, so
Yeah.
maybe let me provide a small introduction. So today we are happy to have another session of our online seminar. Today is our speaker is Vladimir Chernov from Dartmouth College. He will tell us about virtual Legendrian knots and possible relations to causality in Borde Sorkin spacetimes. So please, the floor is yours, Vladimir.
Yeah, so I gave here a talk about the Legendrian links and causality in global hyperbolic spacetimes. So to motivate the Borde-Sorkin spacetimes, I will have to repeat a little bit of an introduction into global hyperbolicity and the usual Legendrian knot theory, which is introduced here by Stefan Nemirovski and myself. So let me try to do it. So Lorentz metric on the manifold is similar to Riemann metric, but Riemann metric is positive definite. And in the Lorentz metric, there are n pluses in the diagonalization of a metric and one minus. So I assume here, of course, that the manifold is of dimension n plus 1. The tangent vectors then divide into three classes. Timelike, which represent movement with the speed slower than the speed of light. These are the vectors such that the dot product with themselves is less than 0. Null or light-like. So these are vectors such that v dot v is 0. They represent movement at the speed of light. And space-like, which is very romantic but not physically possible. They represent movement at the speed faster than light, and they are mathematically given by vectors such that v dot v is bigger than 0. So there is a fourth class, which is called non-space-like vectors, which is exactly what it seems to be. It is not space-like. So it is time-like or null vectors. So the tangent space, the manifold at the point P, has two sheets of vectors formed by non-space-like vectors. And there is a question as to which one is future pointing, right? Because we tell our kids that if they study hard, there is a bright future that awaits them. And there is a natural question as to what future is. So future is just 1/2 of the cone, which is chosen continuously. So you have many, many points. At each of the points, you have a cone of time-like vectors. And the future is just one choice of a continuous choice of a half cone. So this is called time orientation, and the chosen half cones are called future half cones. So time-oriented Lorentz manifolds are called spacetimes. So they're physically universes, and points in the spacetimes are called events. So let me give you an example of something where there is no notion of a future. So this is the Möbius strip with the cones which are vertical. So the reason why there is no future is that if you say that this is a future half and this is a future half, then when you go along the gluing edge, you will see that you have to glue the future half to the past half, and this is not the same. So there is no future on this Möbius strip. So on the first glance, it seems that time orientability is the same as orientability because Möbius strip was counterexample. But it is not, because if you choose the same Möbius strip, but with the time-like vectors which are horizontal, like in this picture, then there is no problem choosing 1/2 of the cone continuously. And this half is called future pointing, of course. And so orientability and time orientability are a little bit different. But it is related to the standard idea that not every manifold is orientable, but each manifold has a double cover which is orientable. So in the same spirit, it is not true that each Lorentz manifold admits a time orientation, but it is true that each manifold has a double cover which admits a time orientation. So if you have something which is not a space-time, you can go to a double cover and it will be a space-time. So what is causal future? Causal future of a point P is the set of all points Q that can be reached from P via a future directed non-space-like curve. Right, so these are all the points which you can physically reach from P. Similarly, you can define J minus of P, the causal past of P, to be the set of all points that you can reach from P going to the past by non-space-like curves. So the important class of spacetimes is global hyperbolic spacetimes, and they are given by two conditions. The first condition is that the intersection of the causal future and causal past of any 2 points is compact. This is known as absence of naked singularities. And the second condition is very romantic. It says that there is no time travel. So time travel is just the presence of closed non-space-like curves. So you can go to the future and return back. And so why is this compactness condition known as the absence of naked singularities? So let me try to explain what naked singularity is. So assume that you take Minkowski space-time. So this is X, this is T, and they choose the Lorentz metric dx squared minus dt squared. And they delete the point, this point. So first of all, the intersection of the causal past and of the causal future of 2 points will not be compact, because if this is the point P and this is the causal past, so this is J minus of P, and this will be J plus of Q. With Q being this point. So then what will happen is the following, that you would have physical trajectories that start at the point Q and go to the deleted point. And then if you place an observer at the point P, so here I put a small observer, then this observer would be able to find information about the traveling particle, because these yellow trajectories represent movement at the speed less or equal than the speed of light, because the slope is more than 45 degrees. Then the point disappears. So you start from the point Q, and then the point disappeared, and all the time before it disappeared, you were able to see the movement of a point. Well, not see, but detect. So in physics, as we know it, such things do not happen. So this is known as naked singularity, and we hope that such a thing does not occur at all. What does happen, however, is when a moving point passes through the reverse light cone of the observer. But at this point, when the moving point passes through the reverse light cone of the observer and disappears from the observable reality of P, there is a common light ray connecting the point P and the moving point. So the point P actually sees the disappearing point. So this is the reason, this is the difference between naked singularity and covered singularity. In the naked singularity, the moving point disappears from the reality of the observer, but at the moment when it disappears, the observer cannot see it. So this thing we prohibit, and this is the known as the compactness of the diamonds J plus of P intersected with the J minus of Q. What does happen once again is when the moving point passes through the light of sight of the observer at P and disappears. This is allowed. So this is the classical definition of global hyperbolicity, and I should make a small remark that if you open the textbook of Hawking and Nellis, which is a classical textbook on general relativity, then you will discover that instead of requiring there is no time travel, they require something a little bit different, which is called strong causality. So the definition in Hawking and Nellis is equivalent to the definition I gave because of the theorem of Bernal and Sanchez. So I'm not saying that strong causality is the same as this condition B, absence of time travel. This is false. I'm saying that in the presence of condition A, condition B gives you strong causality, whatever it means. Now, why are global hyperbolic spacetimes important? Because there is a strong cosmic censorship conjecture of Penrose that says that all physically relevant spacetimes are globally hyperbolic. I do not want, of course, to say that they are per se globally hyperbolic. What is really meant is that the physically relevant part of the space-time is globally hyperbolic. Inside of the black holes, there is time travel, especially inside of the rotatory black holes which occur. But what happens inside of the black hole does not influence us because we are located outside of the black hole. And hence, it does not influence what happens in our universe. So we will work mostly with global hyperbolic spacetimes till we reach the end of the talk, when we will discuss Borde-Sorkin spacetimes. So there is a classical theorem of Geroch saying that if you have a global hyperbolic spacetime, then topologically it is very simple. It is of the form sigma cross R. And topologically, I mean that it is homeomorphic to sigma cross R. Now, each sigma cross T is here assumed to be a Cauchy surface, so which doesn't help much because I didn't define what a Cauchy surface is. But the Cauchy surface is a set intersected exactly once by every maximal non-spacelike curve. So let me try to explain on the level of pictures. So this is my space-time of the form M cross R, this is M cross T, and this is a timelike curve. So what is prohibited is for the timelike curve to intersect the Cauchy surface in more than one point. If every maximal non-spacelike curve intersects a set at exactly one point, then the set is a Cauchy surface. So in particular, we see that a bretzel is not globally hyperbolic. So in the end of the talk, we will reach Borde-Sorkin spacetimes, and the main difference is that the bretzel is perfectly allowed to be a Borde-Sorkin spacetime. So in the beginning of the talk, I will discuss the relation between causality and global hyperbolicity and Legendrian linking. And in the end of the talk, I will reach to generalized spacetimes, which are not assumed to be globally hyperbolic. They will be assumed to be Borde-Sorkin spacetimes. And instead of usual linking, I will be discussing virtual linking. A little bit in the spirit of Kaufman. So the Geroch theorem says that the globally hyperbolic spacetime is homeomorphic to sigma cross R. But as a smooth topologist, you should realize that the natural question to ask is whether spacetime is diffeomorphic to sigma cross R. And after Geroch's theorem, many physicists used Geroch's theorem as if it says that it is diffeomorphic to sigma cross I, even though it didn't say this. And the situation was saved by Bernal and Sanchez again, who proved that globally hyperbolic spacetimes are diffeomorphic to sigma cross R. But Bernal-Sanchez theorem is much later than Geroch's theorem. Moreover, Bernal and Sanchez proved that each sigma cross T is not just a Cauchy surface, but a space-like Cauchy surface. So the restriction of a Lorentz metric to sigma cross T is Riemann. So in a sense, the reason why Lorentz geometry was not discovered long ago was that Newtonian mechanics fits our lifestyle pretty well. And in the Newtonian mechanics, the dot products are positive. So in a sense, you can think that we live on a Cauchy surface, which is space-like. So space of light rays up to fine parameterization is the unit tangent bundle of the Cauchy surface. So let me try to explain why this is true. So this is my globally hyperbolic spacetime. This is a Cauchy surface. This is a light ray. So the light ray is not tangent to the Cauchy surface, so the velocity vector, which is null, so the dot product of the velocity vector with itself is 0, is transversed to the Cauchy surface. So what you can do is that you can do the orthogonal projection of the light vector to the Cauchy surface, and this gives you the direction. Now, the usual geodesics have preferred parameterization. The geodesics on the Riemann manifold, you can always require that you move at speed 1. On the Lorentz manifold, if you have a timelike geodesic, you can require that you move at speed -1. For null geodesics, every affine parameterization is equivalent to any other parameterization. So it is not true that you can choose the preferred parameterization. You can only multiply the parameterizing vector by a constant. This will cause the multiplication of the projection by a constant as well. So the direction of the projection to the Cauchy surface is preserved, but the length of the projection is not preserved. And the direction of the projection to the Cauchy surface is exactly a point in the unit tangent bundle. So we explained that the space of all light rays up to fine parameterization is the same as the unit tangent bundle of a Cauchy surface. But Bernal and Sanchez proved more than Geroch's smooth version, and they proved that the Cauchy surface can be chosen to be space-like, so that the restriction of the Lorentz metric to the Cauchy surface is Riemann. So this means that the tangent bundle of a Cauchy surface is the same as the cotangent bundle of the Cauchy surface. This means, of course, that the spherical tangent bundle of a Cauchy surface is the same as the spherical cotangent bundle of the Cauchy surface. And as Roma multiple times explained to this audience, I'm sure, the spherical cotangent bundle of a manifold has a contact structure, because Roma is a specialist in contact geometry. So let me remind you what a contact manifold is. So if you have a manifold of odd dimension, you could have a form alpha, but the contact structure is not the form, it is the kernel of this form. And the requirement that makes it contact is alpha wedge d alpha to the power k is a volume form, so it is no way zero. So geometrically, this strange condition means that the contact structure is maximally non-integrable. So the dimension of tangent submanifolds is as small as possible. So the maximal tangent dimension is k. So let us look at our example. In our example, the space-time was of dimension m+1. And the space-time was of the form sigma cross r. So sigma is of dimension m. The tangent bundle of sigma is of dimension 2m, and the spherical cotangent bundle of sigma, is of dimension 2m-1. So the good part is that it is an odd-dimensional manifold. So Lowe, Robert Lowe, which is the founder of all the subject, observed that the space of all light rays has a contact structure. It is different from what Roma taught you because of the following, that Roma taught you many times that the spherical cotangent bundle of a manifold has a contact structure. But what Lowe observed is that the space of all light rays has a contact structure. So if you have two different Cauchy surfaces, sigma 1 and sigma 2, then each one of them is identified with the space of light rays. But the identification is not trivial, it is not by parallel transport. So this means that it is not obvious, at least, why the contact structure coming to the space of light rays from the first Cauchy surface agrees with the contact structure coming from the second Cauchy surface, but it does, and this is the result of Robert Lowe. So what about Legendrian submanifolds? So there is a natural question, how many light rays pass through a point? So if you have a point and this is the light cone of a point, then everybody knows that the set of light rays passing through a point forms a light cone. Hungyun, do you have a question or? No. So it has a form of a cone, and this cone is foliated into individual light rays. And the set of individual light rays forms a sphere. The sphere is very easy to imagine because this is the sphere of light rays you can point to if I give you a laser pointer, right? If you're standing in the center of a classroom, I give you a laser pointer and I ask you to point to all possible directions. You will be pointed to a sphere of directions, and this is the sphere I'm talking about. So this sphere is of dimension m-1. So we have an m-1 dimensional sphere inside of the space of flow light rays, which is of dimension m-1. And you observe that m-1 times 2 plus 1 is equal to 2m-1. So what I'm trying to say is that the sphere of light rays through a point is Legendrian. So if you have 2 points in a space-time, you have 2 Legendrian spheres, so you have a Legendrian link. So low conjecture was formulated for space-times of dimension 2 plus 1, which are globally hyperbolic, and with the requirement that the Cauchy surface is an open submanifold, so you do not allow it to be a torus or a bretzel or a sphere. And the low conjecture says the following, that 2 points P and Q are causally related exactly if the link consisting of the spheres of light rays through these 2 points is not deformable to a pair of fibers. Right, so it is a little bit strange, because usually when you talk about knot theory or link theory, you say that the link is trivial if you have 2 trivially knotted circles and they can be placed into disjoint balls. Here, the definition of trivial link is different. So a link is trivial if it is isotopic to a pair of fibers of the spherical tangent bundle. So it does not lead to a contradiction, because in the usual link theory, you never deal with the knots which are not homotopically trivial. So in a sense, if you want to deal with knots or links which are not homotopically trivial, or as in this case, not even zero homologous, you can define the trivial link to be whatever you want it to be. And what Lowe did is that he defined the trivial link to be isotopic to a pair of fibers. There is an Ontario-Todd conjecture. So what is the beauty of the Lowe conjecture? The beauty of the Lowe conjecture is that it is the first attempt to relate linking to general relativity. And if you open a book by Arnold called Arnold Problems, then you will discover one of the problems attributed to Penrose asks pretty much the same question as the Lowe conjecture, but Arnold attributes the question to Penrose. We actually think that the first person who asked this question was indeed Lowe, a student of Penrose, but very likely Low's work was greatly motivated by the works of Penrose. Lothario Todd were the first one who asked the same question in dimension 3+1. So of course, Low was a physicist, so he was very interested in dimension 3+1 because it is physically relevant. But he discovered that in dimension 3+1, his question gives the conjecture is false. He discovered examples of causally related events such that the spheres of light rays are topologically unlinked. He discovered these examples in dimension 3+1. And Low was the first one who discovered that the space of light rays has a contact structure. So he was excellent close to formulating a Ontario-Todd conjecture, which is about Legendrian linking. But nevertheless, the conjecture was formulated much later by Ontario and Todd. So Ontario-Todd conjecture is about space-times of dimension 3+1 with the Cauchy surface equal to R3. I do not want to say that it is isometric to R3. I want to say that it is diffeomorphic to R3. And what the Ontario-Todd conjecture says is that 2 points are causally related if and only if the link consisting of the spheres of light rays through these 2 points is Legendrian non-trivial. So it is not Legendrian isotopic to a pair of fibers. So the motivation for these conjectures is the following. Assume that you have a point Q and the point P, and you assume that they're causally unrelated. So what I would like to do is that I would like to move the point Q along the R fiber of the Bernal-Sanchez decomposition until it is located in the Cauchy surface passing through the point P. So I'm moving the point. On the first glance, it seems that it is not related to link isotopy. But what I'm going to do is that I'm going to say that each time I move the point slightly, the sphere of light rays through this point got deformed. So I fix the shape of the sphere of light rays through the point at each moment of the movement. So then the deformation of a point from this location to this location gives you an isotopy of a sphere of light rays through this point to a sphere of light rays through this point. I claim that if I change this isotopy so that I add the sphere of light rays through the point P to this picture, then this deformation is an isotopy. How do I know that it is an isotopy? Because what is the difference between isotopy and homotopy? In the isotopy, there are no double points. So I need to show that during the movement I described, there are no double points. Assume that there is a double point. Assume that the double point happened at this location of the moving point Q. So this is a double point between the sphere of light rays through the point P and the sphere of light rays through this location. So 2 spheres of light rays intersected. So there is a common point between the spheres of light rays. But this common point, of course, is a common light ray. So I have a light ray from the point P to this location of the moved point Q. So this is a light ray, so I'm moving at the speed of light. And this is a trajectory going along the R fibers of the Bernal-Sanchez decomposition. So in a sense, I'm staying in space and I'm just allowing the time to progress. So the concatenation of these 2 red trajectories is a non-space-like curve connecting P and Q. So P and Q are causally related. But I started with an assumption that P and Q are causally unrelated. So this is a contradiction. So we proved that if you have a globally hyperbolic space-time and you have 2 points which are causally unrelated, then the spheres of light rays through these 2 points are unlinked. So the law conjecture and the Legendrian law conjecture ask if it is really the same, that the 2 points are causally unrelated and the spheres are unlinked. So the direction, one of the directions we proved a few minutes ago, and the other is a conjecture. So some restrictions on the situation are needed still. So the restrictions are the following. That assume that your space-time is of the form S2 cross R with a Lorentz metric, which is a product of round unit sphere metric with minus dt squared along the R component. Then the sphere of light rays through North Pole 0 is the same as the sphere of light rays through North Pole 2 pi. Why? Because I'm talking about the unit sphere. So it takes 2 pi units to go around the unit sphere along the great circle. During these 2 pi units of time, my R coordinate gets changed from 0 to 2 pi. So the sphere of all light rays through North Pole 0 is the same as the sphere of light rays through North Pole 2 pi. So now I would like to look at the following 2 links. The sphere of light rays through North Pole 0 and the sphere of light rays through North Pole 2 pi, because we agreed that this is the same sphere for slightly non-trivial reasons. And the sphere of light rays through South Pole 2 pi and the sphere of light rays through the same point. So these things are identical. Once again, the first sphere is the same for slightly non-trivial arguments. The second sphere just has the same name. So the links are identical, but these 2 points are causally related. And these 2 points are causally unrelated. So why are they causally unrelated? Because they live in the same Cauchy surface, I equal to 2 pi. Why are these 2 points causally related? Because you can go along the light ray from North Pole 0 to South Pole pi, and then you freeze the location and allow the time to progress. So there is an obvious non-space-like trajectory from North Pole pi to South Pole 2 pi. So these 2 points are causally related, these 2 points are causally unrelated, but the links are the same. So this is really why Notarian and Todd required that the Cauchy surfaces are 3, because they were afraid of topology to the Cauchy surface. But as we shall see, the fear is really not based on reality. So similar examples exist if you consider what is called Y-axle Riemann manifold. So Y-axle Riemann manifold is a Riemann manifold such that there is a point x and the number L greater than 0, such that all unit speed geodesics through x also pass through x in time L. So, for example, if you talk about a sphere or an ellipsoid, then the sphere is a manifold yn pole 2 pi. Because all the unit speed geodesics through North Pole also pass through North Pole at time 2 pi. And there is a theorem of Berard-Bergerie that says that if you have a y-axis Riemann manifold, then the universal cover is compact and the rational cohomology algebra is generated by one element. So why do I bring the y-axis Riemann manifold into the picture? Because I gave the example where linking is not the same as causality. As you can deduce from a little bit of thinking, the same example can be constructed by multiplying a y-axis Riemann manifold by R. So there is nothing special about the sphere in the previous example. The only thing that matters is that the sphere was a y-axis Riemann manifold. So what we proved with Stefan Nemirovski is the following: that there is no positive Legendrian isotopy from a sphere to itself, from a sphere fiber to itself. So it seems like a complete jump of logic, because I was talking about causality and then suddenly I talk about positive Legendrian isotopies. But what happens is the following: that if you have a causal trajectory, so this is a causal trajectory, then you can start moving the sphere of light rays through the point on this causal trajectory. And what we proved with Stefan is that this movement is a positive Legendrian isotopy. So it is not just a Legendrian isotopy, it is a positive Legendrian isotopy. And Hong, you have a question? You seem to be talking, but you're muted.
Yeah. Could you repeat what is a positive Legendrian isotopy?
I did not repeat it yet, so I will state it in a second. So a positive Legendrian isotopy is the following: that when you have an isotopy, your object moves. And each point has a trajectory, and each trajectory has velocity vectors. And contact structure is a kernel of a certain one form.
Mm-hmm.
So a positive Legendrian isotopy means that the evaluation of the contact form of the velocity vectors of the moving points is positive.
Yes.
Okay.
Yes.
So we proved that. Thank you for the excellent question. So we proved that when you deform a point via causal trajectory going to the future, then the sphere of light rays through the moving point experiences a positive Legendrian isotopy. So we proved what? We proved that if there is no positive Legendrian isotopy of a sphere fiber to itself, then Legendrian linking is the same as causality. And moreover, we proved that such isotopy does not exist if the universal cover of the Cauchy surface is not compact. Now let us return to Berard-Bergerie theorem. Berard-Bergerie theorem says that if you have a y-axis Riemann manifold, then the universal cover is compact and the rational cohomology algebra is generated by one element. So we see that if the universal cover is not compact, then linking is the same as causality. So we started to see the repetition of the Borde theorem, but in a completely different setup. So we assume that what should be true is that if the conclusions of the Borde theorem hold, then linking is the same as causality. So once again, we were able to show that if the universal cover is not compact, then linking is the same as causality. So we concluded that the reasonable conjecture is that if the rational homology algebra is not generated by one element, then linking is also the same as causality. And this was proved by Frauenfelder, Labrousse, and Schlenk, who really proved more. So they proved that such an isotopy does not exist unless the integer cohomology of the universal cover is the one of a compact rank 1 symmetric space. So what is a compact rank 1 symmetric space? It is a sphere, IPN, complex projective space, Hamiltonian projective space, or the Actonian projective space. So in a sense, this conclusion, by the way, is called contact Borde-Samuelson theorem. I should have said it. So the usual classical Borde-Samuelson theorem has the same conclusion that the universal cover of a manifold is compact and the integer cohomology is the one of a cross, but it deals with the following situation. It deals with the situation when all the geodesics from every point return back at the same time. So the contact Borde-Samuelson theorem is not due to Borde-Samuelson, it is due to Frauenfelder, Labrousse, and Schlenk, who proved it because they were trying to solve the conjecture we did with Stefan. So so there is a natural question. So we proved that linking is the same as causality. But in reality, if you want the problem to become physics, you want to have a computable invariant which will tell you whether the link is trivial or not. So there are plenty of invariants which tell you non-triviality of the classical links. But the classical links happen in R3. In our setup, the linking happens in the spherical tangent bundle. So it is not a classical link situation. And what we proved with Gage Martin and Nina Pitkova is that Havanov homology and Higger-Floyer homology of a 3-component link completely captures causality. So let me try to explain why do we get a 3-component link, because it should come as a surprise. Right before we were talking about 2-component link consisting of the sphere of 2 spheres of light rays through 2 points. So the linking that happened before was happening in the spherical tangent bundle of a Cauchy surface. If the Cauchy surface is 2-dimensional, then it is coverable by R2 with some metric, or it is a sphere. And the spherical tangent bundle of R2 is a solid torus. So how do you get from R3 to the solid torus? You take a trivially noted component which intersects the image of the torus as I tried to draw in this picture, and you delete it. R3 minus the green component is deformable into the solid torus. So before we had a two-component link in the solid torus. But this two-component link plus the green component gives me a three-component link in R3. And what we proved with Gage Martin and Inna Petkova is that the Havanov homology of this three-component link completely captures causality. We proved the same for Higger-Floyer homology. Now, there is a natural question, how about high-dimensional spacetimes? For the high-dimensional spacetimes, personally, my favorite invariant would be Morse flow trees, but I'm just in the process of starting to learn them, so I cannot really prove them. But the papers of Ivan Smith and Tobias Ekholm look very motivational. So now it is time to go to virtual Legendrian links and Borde Sorkin spacetimes. So the classical Legendrian, the classical virtual nodes and links are nodes in the product of a surface by a real line. So these are classical virtual nodes. So they were introduced by Lou Kaufman. And what they are links up to isotopy and one modification. So if you have a surface and you have a link in the thickened surface, so you have this component, you can change this component to a different component obtained by changing the genus of the surface. So you can glue the handle so that the gluing handle does not intersect the projection of the surface, the projection of the link. So let me repeat it. The classical virtual links are links in thickened surfaces. So products of a surface by R. Links here are considered up to the following equivalence relation. You could do a deformation of a link, which is an isotopy, and you could change the genus of the surface. You could change the genus of the surface by gluing the handle. This handle should not intersect the projection of the link. Of course, if you allow to glue the handle, you can also allow to delete the handle. So this is the classical Kaufman's virtual link theory, and unfortunately it does not help. What does help is the theory of virtual Legendrian links, which was introduced by two Dartmouth former graduate students, Cahn and Levi, Patricia Cahn and Asa Levi. So similar to the classical virtual nodes, they can be viewed as generalized Gauss codes, whatever they are, modular formal randomized moves. But the formal definition is that they are nodes in the unit cotangent bundles of manifolds up to Legendrian isotopy. So for the classical Kaufman's nodes, we talk about usual isotopy. So here we talk about Legendrian isotopy and surgery on M away from the front projection of the Legendrian link to the surface M. right? So if you have a Legendrian link, it can be completely described by a front projection. So if the front projection does not intersect a certain location, say this one, then in this location you're allowed to glue a handle. And what we proved with Rustam Sadikov is a version of the Kuperberg's theorem for virtual knots. So if you have two Legendrian knots in the spherical cotangent bundle of S2 that are not Legendrian isotopic, then they are not virtually Legendrian isotopic. So on the first glance, it seems surprising because if you have two knots which are not Legendrian isotopic, you could still probably modify the genus of the surface sphere of the sphere so that it becomes larger. Then you do isotopy, then you decrease the genus, then you increase the genus again, and then you get to the other Legendrian knot. So what we proved is that this does not happen. So if you have two different Legendrian knots, then they're not virtually Legendrian isotopic. So in fact, we proved more. We proved that if you have two Legendrian knots, K1 and K2, located in the spherical cotangent bundle of M1 and spherical cotangent bundle of M2, that are virtually Legendrian isotopic, then you can do the following. You can monotonically decrease the genus of M1 and the genus of M2 till the links become the same. Right, so you have a first link which happens in the spherical cotangent bundle of this surface, the second link which happens in the spherical cotangent bundle of this surface, and then the only operation that we are allowed to do is isotopy of a link and deletion of handles. Then what we proved is that if the knots are virtually Legendrian isotopic, there will be a moment when they will be isotopic as usual Legendrian knots in the same spherical cotangent bundle. So you don't need to increase the complexity of the surface, it is enough to decrease the complexity. So now what is an allowable Legendrian isotope? An allowable Legendrian isotope, virtual Legendrian isotope, is when the manifold M is not homeomorphic to a cross. So it is not, I'm sorry, not the manifold itself, but the universal cover. So we prohibit the virtual Legendrian isotopes during which the universal cover of the manifold M is a cross. So a sphere, complex projective space, Hamiltonian projective space, or Octavians. So what we conjectured with Rustam Sadikov is that if you have a strongly allowable virtual Legendrian isotopy of a fiber So we conjectured the following, that you cannot have a strongly allowable positive virtual Legendrian isotopy of a fiber back to itself. So this is similar to statement one that we proved with Nemirovski. That there is that Legendrian linking is the same as causality if there is no positive Legendrian isotopy of a fiber back to itself. So we conjecture that if you do not have crosses, compact rank 1 symmetric spaces as your manifolds during the virtual isotopy, then you would not have a positive Legendrian isotopy of a fiber back to itself. But you have to require one more condition. You have to require that the isotopy is strongly allowable, which means that the surgery on M, which we get during the virtual isotopy, has index less or equal than 1/2 the dimension of M. It could be possibly less than a dimension of M minus 1 is enough. So why does this second condition appear? The first condition with the compact rank 1 symmetric spaces appears because of the YXLs, which are bad. The second condition appears because of the following, that you start to grow a Legendrian sphere. You do a surgery where you cap this red sphere with a disk. Then what you will get will be a disk with a contracting sphere. And this contracted sphere will contract to a fiber of this point. So if you do not restrict the dimensions of the indices of the surgeries of the Morse function, then you could have positive Legendrian isotopies of a fiber back to itself, and we don't want it. So we introduce two conditions. The first condition is that no compact rank 1 symmetric spaces appear, and the second condition is that the index of the Morse critical points is less than the dimension of the manifold -1. And the generalized Borde-Sorkin spacetimes are the following: that they're spacetimes which are not spacetimes, so they're not Lorentz manifolds. They're equipped with a Morse function, T, which at certain pieces makes the Lorentz metric degenerate. So if you have a Morse function, so here you have a sphere, and here you have a torus, and here you have the Morse critical level. Then the requirement of being Borde-Sorkin is the following: that before the critical level, this piece is globally hyperbolic. And after the critical level, it is also globally hyperbolic. So being Borde-Sorkin means the following: that it is not a space-time at all. So it is a space-time with a degenerate Lorentz metric. But there is a degenerate timelike function such that if you cut out the critical levels of the timelike function, then the left pieces are globally hyperbolic. And the function, the Morse function, is timelike. So the conjecture is the following: that we really conjecture that causality in such Borde-Sorkin spacetimes is the same as the statement that you cannot have a strongly allowable virtual Legendrian isotopy of a pair of fibers to the pair of the links of the line of the spheres of light rays through the 2 points. So once again, the conjecture. Yes.
Just a quick question. So about your Morse function, do you assume that it's a finite type, or it's allowable to have infinite number of critical points?
It is allowed to have infinite number of critical points. But we would be happy to have a finite number of critical points as well.
Okay, thank you.
So once again, the conjecture is about the following: that Borde-Sorkin spacetimes are spacetimes which are cut by the critical levels of the Morse function into global hyperbolic pieces. The law conjecture says that Legendrian linking is the same as causality. The notion of causality is well defined in Borde-Sorkin spacetimes. But we propose that instead of Legendrian linking, we need to consider strongly allowable virtual Legendrian linking. So let me remind you what these words mean. So strongly allowable means that you prohibit the Cauchy surface to become such that the universal cover is a compact rank 1 symmetric space. Strongly means that the indices of the critical points are not more than the half of the dimension -1, +1. And virtual means that you consider Legendrian isotopy plus modifications of the manifold in the spherical tangent bundle of which you live. The modifications are by surgeries that happen away from the front projection of the Legendrian manifold. So this is the conjecture, and we prove this conjecture in dimension m, equal to 2. So in the toy dimension, we prove the conjecture. This is a theorem in our recent paper in Geometry and Physics. And for other dimensions, it is a conjecture. And this is the end of the talk. So are there any questions?
Yeah, maybe one extra question. So whenever you spoke that you would like to use this Morse gradient flow trees, if I understand correctly, you would like to use them in high dimensions. And
Yes.
Okay, so maybe I don't completely understand the reason, but typically, if you would like to interplay between something like a holomorphic curves and gradients and the gradient flow trees, then somehow in high dimensions you could potentially face a problem because of somehow different types of degeneracies for holomorphic curve that will not happen for the gradient flow trees.
I'm not sure that I'm right about Morse flow trees. It's just that I'm trying to think about a computable invariant of Legendrian links that works in high dimensions. And it works for the spherical cotangent bundles. Mm-hmm. So there are many computable invariants which work in Euclidean spaces. But this is not what we need.
Yes. Are there any other questions, comments, remarks? If there are not, we would like to thank you, Vladimir, for the great talk.
Yeah, and I still hope to visit Prague one day in person.
Yeah, we would love to. We would love to invite you, and we'll be happy if you would come at some point. So, thanks a lot.